This is a strength of material problem where we have three steel plates of 25 by 150 millimeter cross section. They are welded together to form this H shaped column. Later, for architectural reasons, they remove a 25 millimeter strip from each side of one side of the H column. We know that the maximum allowable stress on the structure is 100 megapascals. Now they want us to calculate the forces that can be applied to the original structure where we don't have this cutout, and later after we do this cutout and the force remains centric to the original H shape, so the force will not move, it will always be applied to the same location. Okay, let's see part A first. They want us to find what kind of force can we apply to the structure with its original shape intact without this cutout. So for that we're gonna rely on the normal stress, which is, as you see it in this sketch, we have an area and the force pulling upwards, so stress equals force over area. But here we have a compressive stress, so therefore we're gonna have to throw in this negative force over area. Now we calculate our force, plug in our values, and there we go. Force equals 1.13 meganewtons. Here, as we notice, our force is a centric force, centric loading. So that means this structure is symmetric and the force is applied at its neutral axis, at its center. Now in part B, when we're gonna cause this change in the structure, this will move things around, and what's gonna be moved is the neutral axis of this structure. It's not gonna be a symmetric structure anymore, it's gonna be different. We're gonna have a top section that's the original size, but the bottom section will be much smaller. This cross section where we're gonna do our calculations is not at the top anymore, it's lower down here where we have this smaller section on this side, and therefore this is not symmetric, so the neutral axis is not at the center anymore, it will move, and this move will cause our force to become an eccentric force, an eccentric loading. So in order to do our calculations, we first have to find where our neutral axis is. Okay, in order to do these calculations, to find our y bar, I like to make a nice little table where I can calculate the area, the centroid, and the first moment of each moment of inertia of each body. Like this, we can have a sum for the areas, we can have a sum for these, and then therefore the centroid will be equal the sum of this one over the sum of this one, and we are able to find our neutral axis. I marked number 1 as the top bar, 2 the middle, and 3 as the bottom. Now usually we like to, when we start these calculations, we need to assume an axis somewhere. So I assumed my axis for our calculations in the middle of this structure. So wherever this body's center is, that was where I laid my x-axis instead of down here at the bottom. We can also see this here, since number 2, the y bar of number 2 is 0. Now that we have our centroid, let's take a look at what formula are we heading towards. So the stress with an eccentric axial loading, our formula would be as such. We practically combine the axial loading with the bending stress, so these two together will give us this formula. And now we have our y bar, so we can go ahead and calculate our I, our moment of inertia. In order to find that, we're gonna break our structure up into 1, 2, and 3 pieces. So inertia of 1, inertia of 2, inertia of 3, sum it up, and we have our final inertia. So I'm gonna take each, use the formula from the back of our box. We can rely on these, and we can go ahead and calculate our inertias, but in the same step, I'm gonna go ahead and move each inertia to the neutral axis that we found earlier. This axis, this 10.938 millimeters that we have found, remember that we assumed our initial calculations from the center, so therefore this will be 10.938 millimeters above this center right here, so it's not from the bottom of the structure. So if we look at this little sketch that I made on the side over here, we can see that this will be my neutral axis right here, somewhere above the half of this structure. So this is my NA, neutral axis. That's what we're gonna move. We're gonna calculate inertia of this piece, move it down to here, this piece move it up there, this piece move it up there. Here are the calculations. This is plus area times distance to the square. Each shape on its own, and on the end we are able to sum them up and find our inertia to be 5.40 times 10 to the negative 5. Each of these calculations, first I left it in millimeters, so therefore you would get millimeters to the fourth, but to save on space I went ahead and converted it to meters to the fourth, and therefore that's how we get this number. Same here, same here. Now let's take another look at our formula. Stress, we have it, it was given 100 megapascals. Area we have, the moment we have, it's just force times the eccentricity. The y we have, the I we have. So all we have to do, solve for P. First we're gonna plug in for M right here. This is my formula. Again, remember the formula is with tensile load, so therefore we're gonna have to include a negative right here. And from here we're gonna first take a look at our moment. Moment is force times distance, and our force is applied at the eccentricity. So that would be the distance from wherever it's applied to the neutral axis. And that is this distance for us. That is from our center of here, where it's applied, to the neutral axis. And this is the same number that we have found, the 10.938 millimeter distance. So we know. The P we are interested in. So from here we can go ahead, factor it out, and we are able to solve for it. Now we have a nice multi-level chaos over here, but everything that we have, we know it. So all we have to do is plug it in, go to a calculator, and we are able to find our force, which is 0.817 meganewtons. And as a final check, we can go ahead and compare this one to what we found in the original shape. We can see that in the original shape, when we didn't have a cutout, our force was that was allowable was 1.13 meganewtons, and after we cut some pieces out of it, the force dropped down to 0.817 meganewtons, which is common sense. We made it smaller, we made it weaker, so therefore it's going to be able to take less force.